Record. Okay. So yeah, we'll define degrees of freedom sort of again, it's going to be a more loose definition because degrees of freedom does depend on like which subject you're talking about. For example, in classical mechanics, what a degree of freedom is would be very different than what it would be in like quantum field theory, for example. Um, because fields have, as we'll see, classically infinite degrees of freedom, but having an infinite degree of freedom is not a useful concept, right? So, it's useful to look at it from like different perspectives. So in classical mechanics, I can define it through an example like this. So in classical mechanics, if I can spell, okay. So say we have a ball and all I can do is move down. Okay. So it's sort of confined to like the line it's on, and all the forces are like parallel or perpendicular to the sorry, parallel to this line. Okay. Um, so in this case, I have 1 degree of freedom, 1 degree of freedom for my position, right? I have 1 degree of freedom for my position, but I have another degree of freedom for my velocity, right? So I have 1 degree of freedom for where I, for example, initially start, and then I have another degree of freedom for how fast I initially start. So those are my degrees of freedom. And these two things, um, they determine the motion that my particle will take for the rest of time. And so,
So in a field, when you have, in a quantum field, when you have quantized vibrations, and
Mhm,
we're talking about degrees of freedom,
mhm.
we're talking about the freedom the vibrations or the wave function can take.
It's more about how many fields do I need to describe this particle. So, for example, you have one particle that defines the field itself, then you have one field for its spin. You have one field for, I don't know, like its physical angular momentum and stuff like that. So, in a quantum field theory sense, like the definition of degrees of freedom are a lot more like it's a lot more varied. But we won't really talk about QFT. So I think having this definition for degree of freedom is okay. Another thing, so uh, when we talk about this more generally, what we'll see is that we have degrees of freedom. Degrees of freedom will be the dimension of like dimension of the dimension of like the configuration space. So in
Sorry,
this
can you repeat that? Oh,
Yeah, so the number of degrees of freedom will be the dimension of the configuration space plus the dimension. Well, okay, it's going to be two times. It's going to be this number times two. And to think about it, so configuration space you can think of for now as just the space of all possible positions that my particle can take. So, for example, if I'm confined to a sphere in 3 dimensions, I only have 2 degrees of freedom, even though I'm moving in 3 dimensions. Right? Even though I'm moving in 3 dimensions, I can only really change my like azimuthal angle and my polar angle. I don't have much more degrees of freedom than this. And I don't
so
have a
why,
degree.
why wouldn't you define degrees of freedom based on, okay, so we're describing degrees of freedom using spherical coordinates. Is that simply because we've just restricted ourselves to the sphere?
Mhm.
Or
So if
that
I mean,
so if
okay,
I
so
defined us on a cube, if I defined a cube, for example,
are you on the surface of the cube or are you like on the
let's say we're in the cube. Let's
okay.
say we're in the cube, we're starting from the origin, it's just a
Mhm.
unit cube.
Mhm.
So then would I have 3 degrees of freedom because I can move along the X plane, along the Y plane, and along the Z plane?
Yeah, so you have 3 degrees of positional freedom, and you have an additional 3 degrees of like momenta freedom, right? Because your positions don't really depend on like your positions don't really determine what your momenta are, and your momenta don't like determine your
Yeah,
position.
yeah, because they're independent of each other.
Yeah, exactly. So in that case, you would have 6 degrees of freedom, which is 3 times the dimension, whatever that is, of your configuration.
Oh, okay, okay. So it's just because that we have 3 different displacement movements and we have 3 different momenta
Hmm.
movements,
Yeah.
for lack of a better word. And because of that, there are 6 total degrees of freedom.
Hmm.
But on a sphere, we only have two because the displacement varies with the angle, which is two.
Yeah, so I can only move like azimuthally or polarly, right? There's any other movement on the sphere can be described using these two coordinates.
Oh, okay. So even our momentum and rotation, well, I guess rotation is pretty implicit, but momentum can be described using the angle.
Mhm. Yeah, because
Oh.
again, like what is a momentum, right? So we'll define like the momentum as a conjugate to the position. And what that means is it is a linear functional on the tangent space at a point. That's how we'll define momentum, and we'll see that that definition makes sense in some setting. Okay. Again, in quantum mechanics, you define momentum completely differently. You define it in terms of commutation relations and as a certain like linear operator on state space that does XYZ things.
Yeah, because it doesn't hold for spin of an electron, and then we wouldn't have.
Yeah, exactly. And we'll see that those issues that happen in the quantum world already happen in the classical physics sense, but because we're working on like a nice space, on a finite dimensional nice space, those issues are sort of hidden.
Yeah,
Um,
oh yeah. I see what you mean because like when you derive Newton's law from quantum mechanics, you
mhm.
can kind of see that because, you're not in the seventh dimension.
Yeah. So so a way to think about this is classical mechanics is so the classical mechanics that we have is a smooth approximation for how the real world actually looks, right? The real world isn't smooth. Okay. Now, because we're so much larger than like the Planck length, it makes absolutely no difference to us if we approximate as a smooth surface or as a discretized surface. And it just turns out that we are much nicer, like we're much happier working with a smooth system than a discretized one. However, when you go down to the quantum world, now you're not that much bigger compared to Planck length or Planck scale rather, right? You're no longer you're no longer big compared to that. You're around it or just slightly bigger. And now these discretization issues start actually showing up. So as we'll see, when we talk about classical mechanics after we've defined what a manifold is, um, we'll define something called a Poisson bracket. A Poisson bracket is basically the commutation relations that you see in quantum mechanics, but for classical mechanics. And that's the way Hamilton initially described like his equations of motion for classical mechanics. It's in terms of, okay, you take like an energy function that we call the Hamiltonian, and then its motion is just the Poisson bracket. Um, so the motion of a particle is just the Poisson bracket of um, position with this energy function. And we'll see within like certain nice symmetries, um, if our like Hamiltonian function has certain nice symmetries, we get certain nice conservation laws. Um, but we'll also see that in another way. We'll talk about that in two different ways. So yeah, degrees of freedom basically are just how many numbers do I need to give you to be able to describe later motion of my particle? And it turns out that this number is two times the dimension of configuration space. Um, and later on, if we are constrained to a manifold, smooth manifold, M, then DOF equals dimension of the so-called cotangent bundle. Um, so this is the dimension of the cotangent bundle, dimension of the cotangent bundle. Okay. Um, okay. Does that sort of make sense?
Oh yeah, 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 yeah. Okay, okay. I see what you mean. Okay, I see what you mean.
Yeah. So if we're constrained to move along a certain surface or a certain object, then the number of degrees of freedom is just how many degrees, like how many numbers do I need to describe where I am, and how many numbers do I need to describe how fast I'm going. That's
Right.
basically
Okay. Yeah, yeah, yeah. Because everything follows from those two fundamental.
yeah, properties of a particle or whatever.
Okay. 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 Actually, that makes a lot of sense. Yeah. I just wanted to ask because everyone is talking about this. Like, I mean, in like we're only in second year, and everyone's kind of using this loose notation of, oh, this is a degree of freedom.
Yeah.
Okay. That's nice. What does that actually mean?
Yeah, I mean it just means this. And we'll see that like the more constraint equations you add to my like to the manifold, the lower the degrees of freedom become. An example of this already is okay, if I'm constrained so that my norm is one, that's one constraint equation. And it's already dropped my degrees of freedom by two because it dropped the degree of freedom of my position by one and the corresponding momenta by one. Um, okay. Um, okay. Now that we have that, okay, yeah. So yeah, the question about can I deform my like whirl line into like a straight whirl line so that I had basically no impact. Um, that is a fundamental question when we talk about like what possible statistics do we have. Um, so okay. So okay, yeah, we know that. Okay, so if I take some topological, so let X be a topological space, and let P be in X. Then last lecture we define that should be in. So we define pi 1 x comma x as the set of okay, so it's the set of equivalence classes where gamma is a curve from S1 into X such that gamma of 0 is X. Okay. And a loop gamma is equivalent to a loop beta if they're path homotopic. Basically, what path homotopic means is that if I draw out the loop, so if I have this loop, for example, and I have this loop, say this is gamma, say this is beta, can I continuously deform gamma into beta, keeping the endpoint fixed? So if I keep the point x fixed, can I take gamma and smoothly make it beta? That's
So, okay,
yeah.
just for clarification, so this space that we're defining
Mhm.
is just all equivalence classes.
Mhm.
We can take gamma and make it rho, or sorry, what
Yeah,
is that?
beta.
Or beta and make it gamma.
Mhm. Yeah. just by like continuously moving it around and like stretching it, but no tearing is allowed.
Can I compress it?
Yeah, yeah. You can do anything as long as you're not tearing the loop and it's continuous.
Oh, okay. Okay, okay.
Yeah.
Okay.
So an example where we okay, so an example, let's do an example really quick. So the fundamental group um at the point one, let's do at the origin for R2. This will be the loop that contains only one point, and I'll call that point zero. And now, so me saying this is equivalent to saying I can deform every loop based on the origin to any other loop based at the origin, right? So it's a pretty strong claim, but let's see how to do that. So say I have some loop like that and another loop like that, gamma, beta. I know that my space, but in my space, I have so my space, any 2 points, the line between the 2 points is in this space, right? So if this happens, we say that the space is convex. Um, I won't write that, but whatever. Okay. So now what I can do is I can define a map from 0, 1 cross S1 into R2. So okay, this path homotopy thing is equivalent to me saying that I have a map, I have a function, continuous function h with the property that h of 0, 1 equals gamma of 1. H of 1, 1 is beta of 1. Okay. Um, and now what I do is I take a point, so I define h of s comma theta to be, let's see, so I take a point, so here this is say gamma of theta, and let's say this is beta of theta. Yeah, beta of theta. So now I know that this line is completely contained in the space, right? I know
Uh-huh.
this line joining gamma and beta of theta, gamma of theta, beta of theta, oh my God, is completely in our space. What is this line? Well, this line is precisely 1 minus t times gamma of theta minus t times beta of theta. Sorry, plus t times beta of theta. And then this is so here t is between 0 and 1. Let's check that this makes sense. So if t is 0, this term is 0, and this is 0. So all we're left with is gamma of theta, right? And if t is 1, this term is 0, and this term is 1. So all we're left with is beta of theta. And this is linear in t, so it must be a line that starts at gamma of theta and ends at beta of theta.
Out of curiosity,
Mhm. Hello?
hello, hello, welcome back. Welcome back.
My laptop, like, my laptop's been having like Wi-Fi issues. I'm not sure why.
Oh,
Okay.
okay. My question was, if I wanted to like define some squiggle
Hmm.
between like some non-linear function
Hmm.
between phi theta and beta theta,
Hmm.
like say I wanted to define like a cosh function
Hmm.
between the both of them,
Sure.
what would that look like?
I mean, I haven't really thought of it because for the definition of path homotopy, we just required there exists a path homotopy. Again, you could probably define something, but I think that would just overcomplicate like a very simple scenario.
Oh, okay. So we just want like any shape we want the simplest shape between two.
I mean, we want the simplest because if we have an easy one, it's easy to work with. It's easy to define usually, right? In this case, all I had to do is all I have to do is I have to move the curve gamma along a line. That's all I have to do, and that like suffices. So yeah, our path homotopy is given by 1 minus t gamma of theta plus t times beta of theta. And then one can check that this is continuous. Um, one can check that this is a path homotopy, whatever. And I made no assumption of what gamma is. Um, so this should be t here. I made no assumption of what gamma is and what beta is. So this tells me that every two loops are homotopic to each other. So in some sense, our space R2 is very nice. And this should be expected. I mean, R2 is very nice. Okay, we say definition. We say X is simply connected if X is connected and um, pi 1 X X is trivial. And by trivial here, I mean like the one element group. Also, I didn't say, but like the first fundamental. So this object here is called the first fundamental group. First fundamental group. Okay, it's called a group, so it must have a group operation. The group operation is given by concatenation. Concat only. Yeah, I don't know how to spell concatenation. I'm gonna guess it's like that. Um, yeah, so it's given by concatenation, and then you can check that if you you can check that this is well defined. Check that this is well defined. Um, there's you can check in Moncrief's in chapter 9 that he proves that this is well defined. He proves that it's a group. Um, okay. So we call a space simply connected if it's connected and for any choice of base point, the fundamental group is trivial. You can check that if X is simply connected, if X is simply connected, um, then pi 1 of x is equal to pi x of y for any xy. More generally, if um, if x is path connected, path connected just means that between any two points you have a path. So there's a continuous map that takes one point to the other. Path connected, then pi 1 x is well defined. What I mean by this is you don't need to describe a particular point um, to talk about the fundamental group. So you can just talk about the fundamental group, even though for each point in your space you have a different fundamental group. Well, technically different fundamental group. Okay, so let's see an example of a space that is not simply connected. So the space R2 minus the origin is not simply connected. Okay. So this is pretty surprising because removing one point has now made us go from being simply connected to not simply connected. And the issue here is any closed loop sort of has to encompass this encompass the origin. Actually, it doesn't. I mean, you have like this loop, for example, that doesn't have to encompass the origin. But the issue now, I think you can see is that if you have a loop that encompasses the origin and you have a loop that doesn't encompass the origin, there's no way to continuously map one of the loops onto the other. Because say I want to deform the yellow loop into the white loop, right? If I want to deform the yellow loop into the white loop, at some point I have to go through the origin, right? But I can't go through the origin. So it's not simply connected. Um, we'll see that the fundamental group of this space is actually the integers. So basically what this means is that every loop is defined based up to like the number of points it goes around the origin. In complex analysis, this is called the winding number. Um, we don't really have much use for this, so I mean it's just a fun fact. This is also the fundamental group of the circle. Um, and to sort of understand why this is the fundamental group of the circle, um, you can check that R2 minus the origin and S1 are um, are like equivalent up to like homotopy. Um, so I mean you can look this up. This is called homotopy equivalence. But again, we don't really have much use for homotopy equivalence. All you need to know is that it exists. So okay, going around so yeah, the fundamental group, the first fundamental group sort of picks out spaces that have holes in them, essentially. As you can see, like R2 minus a point has a hole in it, so it picks it out. But R3 minus a point also has a hole, but the first fundamental group can't pick that out. And the reason for that is imagine I have a hole in like space and have a loop that like encompasses the hole. I can just sort of pivot my loop around and then deform it back. So it's equivalent. And all I have to do is I have to move around like that, and that won't make me go through the origin, for example. Yeah, so this gives you a quick proof. So quick proof that R2 um, is not equivalent to Rn unless n equals 2. Um, Similarly, R is not equivalent to Rn unless n equals 1. We have a similar argument here. If you remove a point from R, you get two disconnected pieces. But if you remove a point from any other Rn, you don't get two disconnected pieces. Um, so there's a fact called equivalence of domain that says Rn is topologically equivalent to Rm if and only if n equals n. Okay. We won't prove this fact because the proof is very, 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 very non-trivial. Um, but we will use this in our definition of a manifold um, for well-definedness. So it is important to know it exists. Okay, are we happy with this?
A
Okay.
little, because I want to know. I would like to know why the proof is a little untrivial, and where can I find it and prove it on my own?
Um, why is it non-trivial? Okay, so I mean it's non-trivial because it already took us defining an algebraic structure that was totally independent. Actually, it's not totally independent, but when you're first like studying topology, right, you wouldn't have thought to define an algebraic structure that is that could differentiate between non-homeomorphic spaces. That's where the non-triviality comes in. It's because the additional information you require doesn't, I mean, it's very hard to firstly think of. Um, and I'm not sure how the proof is done. I think it's just looking at higher fundamental groups, if I was to guess. But but yeah, I don't know. And also like there's a lot of details that I've missed here. Um, that I haven't talked about. And that's why the proof seems sort of trivial for the R and R2 case, because there's a lot of background that is, it's already assumed in it. With the other ones, it's just because like it was already non-trivial in the R2 case. And R2 is like R2 is intuitively the space we work with all the time, right? So yeah, that's just it. It's like even such a simple problem introduced required us to use algebraic topology um, to solve. So I can't imagine how hard it must be if you like go up in dimension.
Well, I will reconvene with you next week. I have a friend that's really into topology, and I keep inviting him to one of the lectures because he'd really enjoy it, but he's busy.
Yeah,
So
no
I'm
worries.
this proof. We're gonna do it this week, and we'll get back to you.
Okay, okay. I mean I would love to see it. Um, I don't think I've ever like seen a proof. I know it's like non-trivial, but I mean I haven't really because I haven't really looked much into algebraic topology outside of like what I've required. And the first fundamental group in physics usually suffices. I haven't really seen, I mean, I'm specifically saying the first fundamental group because that is you like that I think that entails that there's higher fundamental groups. Um, one interesting fact that I do know about though is um so the first fundamental group may not be abelian, but higher fundamental groups are always abelian. Um, and the reason higher fundamental groups,
Bijective, right? Or sorry, the group is commutative.
yeah, yeah, yeah. So, um, I'll send a proof. There's a really cool algebraic proof of that fact. If you want the first step to it, I will outline the step. Just give me 1 second. Let me write it down. I'll also send a link with I think it's like 50 questions I've done over the last 3 years of undergrad that I've found. It's 42 questions that I've done over the last 3 years of undergrad that I thought were interesting enough to type up. I'll send that link.
A
Um,
bit of a bit of an unrelated question then, since we're kind of on this subject. Um, Actually, two. So first of all, what sort of lectures would you recommend sitting in on?
I mean, it depends on like what you want to do, right?
Well, for this sort of class, I'm going to call it a class because that's exactly what this is. Like for this class, what sort of higher year lectures would you recommend sitting in on?
So you could sit in on, I'll tell you the U of T course code. So you have MAT 327, MAT 1301, and MAT 425.
Oh, is 425 the Hamiltonian mechanics
No,
class?
that's 461. 425 is differential topology.
Oh, okay. I have to
Um,
take that in upper year anyway, so it'll be nice to
that'll be fun. Okay, so yeah, so say you have operations X and O times that are unital, binary operations on set M, and you have the following. You have A times B times C times D is the same as A times C times B times D. Um, then X and this fancy X are the same. Okay. And you have something stronger. You have that, you must have that X and this fancy X are associative and abelian. Okay.
Is that supposed to say that are initial binary operations on set M?
Unital.
Oh, unital. Sorry, I thought that said initial. Okay.
Unital just means that there exists an element E such that A times E equals A, and there exists another element W such that A, this fancy W equals A. So yeah, if
Okay.
you have unital binary operations such that this thing, this weird looking expression holds, then the operations are actually the same. Moreover, you have that they must be associative and abelian. You can use this to then show that higher fundamental groups are abelian. Um, okay, so now let's take let's move away from all of this. I just wanted to make sure that you guys know what the fundamental group is, because now
Oh,
we're
wait, don't go that far down.
okay.
Thank you. Yeah. So just two questions. So why doesn't this also follow for the first fundamental group? Because if you have these binary options on the set M, and
Mhm.
we can define the set M to be um, the set, like the set containing or the group containing the first fundamental group,
Mhm.
then we can define the binary operations as X and the exotic multiplication is what I'll call it, to be that. And when does that case fail?
Um, so every nice topological space has an abelian fundamental group. As we'll see, um they don't have an abelian one, but they do have a um countable fundamental group. So manifolds have countable fundamental group. The reason it doesn't fail for the higher fundamental groups is because you have an extra degree of freedom that you don't have in um, like the first fundamental group. It's because I don't think there exists such an operation on most fundamental groups. I can't think of any fundamental groups off the top of my head that are non-abelian. Let me look it up. Non-abelian fundamental. Because every fundamental group that I can think of is abelian. Oh, okay, okay. There's a very simple example, actually. Um, so say you have this circle and you have another circle that touches at a point. It just touches here. This space is denoted S1 wedge S1. This space has a non-abelian fundamental group. This has a non-abelian pi 1. And the reason for that is, okay, imagine you traverse one of the circles clockwise and then you go on to the other circle counterclockwise. There's no way, I mean, this map, like going clockwise in one and counterclockwise in the other is different from going counterclockwise on the left one and then going clockwise in the first one because there's no way to deform them. So what I mean is, okay, so say our first one is going like that and then
Uh-huh.
that, okay? And then,
Oh, okay. Okay, I see what you mean.
uh, and And then the second one is you first go like that, and then you go like that. There's no way to deform the red loop into the into the yellow loop.
Because they're always opposed to each
Yeah, I
other.
mean, yeah, the idea is that you need this loop to be second somehow. So you have to like flip everything. But
But even when you
that's
flip it, then you'll have the problem of the one on this side being first, and that also needs to be second.
yeah, and the only way to really get around that is if I broke the loop at say this point, then deformed it into the other circle, and then, so I have to do a non-continuous operation. So there's no, so yeah, this has like a non-abelian fundamental group. The fundamental group for this is actually very disgusting from what I remember. It's like Z amalgamation product Z. It's like it's not a good group uh to work with um from what I remember. There's also an important theorem for the first fundamental group called the Seifert-Van Kampen theorem. I won't describe it because it's very um I mean it has a long statement, so I don't you can look it up. Um okay. Are there any other questions about the first fundamental group?
No, actually, that kind of makes sense. So
Okay.
we construct other any other nice first fundamental group. Is that specifically just for first fundamental groups?
Seifert-Van Kampen?
No, no, no. Just like the non-abelian.
Yeah, the non so only the first fundamental group is non-abelian.
Okay,
Every
and the
higher
rest
order.
are.
Huh?
The rest of them are.
Yeah, the higher fundamental groups are.
Okay.
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 So now let's get into the physics. Like where could we possibly use this in physics? Also, we will go over time. I guess we'll end at 6:30 if that's 7:30 if that's okay.
Of course.
7:45-ish. Okay. So let's go back to R3, right? Say we have two indistinguishable particles, say they're here and here. And moreover, we don't allow like both the particles to be on top of each other at any time. Okay. Now let's let's exchange them. Okay, okay. So before I get ahead of myself, I can dis sorry. I can describe this system with a wave function, right? Um, I can describe it with a wave function like this, right? Now, let's think about this. If I swap the particles through some process, I don't know, this is what their world lines sort of look like. And since they're indistinguishable, my wave function should change only, so my probability should remain unchanged, right? Um, so my probability should remain unchanged. This means I must have multiplied my entire wave function by a complex number of norm 1, right? So this goes to e to the I theta times psi of R1, R2. And then if I exchange them again, so say now, okay, I'll draw it like this because okay. Say I exchange them again, then I pick up another phase factor. But now I know in 3 dimensions, because of like some things we'll see later on, I know that um I have to get back at like exactly where I started. So what this tells me is that my initial function and my ending wave function have to be the same. And because they have to be the same and the wave function is not always 0, what this tells me is that e to the 2I theta has to equal 1. But I know the solutions to this. I know that 2 theta must be 2n pi, where n is in the integers. Okay. So this tells me that my allowed values of theta are n times pi. Okay.
Sorry, could you just repeat that last part? Oh, well, the last part is you're only allowed for e to the 2I pi, right? Because it's norm 1, right?
Yeah.
So you're allowed them equal to 1.
Yeah. So each exchange picks up a factor of e to the I theta because I have some like scalar representation of a certain group. as we'll see, the group that's acting on this is actually the first fundamental group of some other space. Um, okay. So so yeah, the allowed values of theta are just n pi. That's it. Where n is a integer. Okay. So this is the case in R3. So now, okay. So now if n is even, let's do the case where n is even, right? If n is even, what this tells me now is that when I do my first exchange, right, I get a e to the I theta psi, whatever r. Sorry, this should be R2, R1. Sorry about that. And this should be R1, R2. Okay, that's good. So I go like this. Actually, it doesn't matter. What am I saying?
Wait, why is R2 R1?
Yeah, no, no, no. I made a mistake. My bad. It doesn't really matter. Like all the information of the wave function is inside this variable psi. Okay, so when I do my first transformation, I know that n is even. So this gives me e to the I n pi psi r1 r2. But if I draw the unit circle, right, and if I have n times pi where n is even, I can sort of decompose that further into I times 2m times pi, right? Because n is even. But then I know that e to the 2 pi m must be 1. So this thing is 1. So I'm left with this. So okay, under a swap, when n is even, I get the exact same wave function. Okay. So swapping two identical particles does not affect my wave function whatsoever. Particles that obey this exchange statistics are called bosons. So this is the definition of a boson, is that if I have two identical particles in R3 and I swap their positions, um, then my wave function is exactly the same.
Oh, so that's what it means for n to be even. You're swapping the same particle.
No, no. So okay, this swapping motion, right? This swapping thing induces an action on my state space, right? And the allowed actions, or in other words, the allowed representations, right, are multiplication by e to the I times theta.
Sorry, the allowed what? The allowed.
Representations
Okay.
are multiplication by e to the I times theta for some theta. Now,
Oh,
if
that's
this,
what the norms represent, right? Because there's only one representation. Okay.
yeah. So, um, and then we figured out that in this case there's only two real options, right? It's theta is n times pi when n is even, and there's theta equals n times pi when n is odd. Those are the only two real possibilities, right? So when n is even, um, this exchange action is the trivial representation. It does nothing. Like swapping particles does absolutely nothing. So if my particle that I determined by experiments, if my particle doesn't change, um, like if it doesn't even get a phase factor when I swap, then they're bosons. If n is odd, if n is odd, yeah,
Your
then
firm.
n is this for some m, and then doing this exact same thing. Um, Doing this exact same thing, I get e to the I times 2 pi, 2m pi, e to the I pi, psi 1, sorry, psi of R1, R2. But this, as we saw above, is 1, and e to the I pi is minus 1. So, okay, in this case, swapping Particles induced a -1 phase factor in my wave function. Particles that satisfy this are called fermions. So for example, electrons are fermions, right? Um, if you guys have taken 252, have you guys
Taking
taken?
it right now. Right now.
Okay, yeah. At the end of it, you'll learn like statistical mechanics. Um, and in statistical mechanics, like in the statistical mechanics you guys will talk about bosonic um, particles and fermionic particles. Bosons, from what I remember, are not too interesting when it comes to this. Fermions, on the other hand, are interesting because you pick up a -1 phase factor. Um, so they're like semi-interesting. Okay. So as we see in like three dimensions, um, I mean, in terms of math, nothing interesting is happening, right? Um, your your group that acts on this space, like the um, exchange thing that acts on this space is gives you a trivial representation, right? It's not a fun representation. But things change in two dimensions. But okay, so let's define some objects a little carefully so we can talk about this in more generality. So okay, say we have some topological space X. So let X be some top space. Okay. This will be our like space where we confine the particles. Okay. Um, Later on, these will be smooth manifolds, but for now, we're happy with being topological spaces. Okay. And now, if we look above, what space are we actually looking at? We're looking at this space of all points, all tuples of points, right? Because we need to know where particle one is, where particle two is. So in such a way that the two positions are not the same. Right? You can't have particle one being on top of particle two. That isn't allowed. Okay. So we define the configuration space of n ordered points in X. Okay, so we're gonna call this space. We're gonna call this we're either gonna call it C with a hat n x, uh, which is the same thing as conf n x, and it's going to be the set of points x1 up to xn in X cross multiplied by itself n times, such that xi doesn't equal xj um, for I not equal j. Okay. So it's basically you take n points. Um, Sorry, say you have n points in your like confined to this space. You're looking at the set of all possible positions of these particles, essentially, because you can't allow them to be on top of each other, for example. Does that make sense?
No. So the little x are the particles,
Positions of the particles.
positions of the particles. Okay, and you're looking for all ordered points
Mhm.
of the positions in the particles such that they're not on top of each other.
Yeah. You're
Oh,
it's basically you take a space, you like look at everywhere they could be, right? And this is like an n tuple of points. And you impose the additional constraint that two particles aren't allowed to be on top of each other. That's what the configuration space is telling you. Okay.
okay.
Now, um, if you look at the group Sn, which is the group um, so it's the group of bijections of like this set. This is called the permutation group because it takes like a list of n things and it just permutes the order. This is called the permutation group. Okay. So now the permutation group has a canonical action on configuration space. Okay. So S1, oh sorry, Sn acts on configuration space. And the action is given as follows. So you take a permutation sigma, and you feed it a point x1 up to xn. And then this, all it does is it permutes the particles. Right? So it sends like that. And
Is this the same one from the first lecture on Saturday,
first lecture on Saturday.
where was the matrix representing?
I think there we only talked about, yeah, yeah, the word group action means the same thing. Yeah.
Okay, okay, okay. So sigma is just group action.
Yeah, so it's a typical group action. So you can check that this is a left group action of Sn on configuration space. Because remember, a group action just takes a set X, it takes a group, and then it acts on the group in a nice way. Um, so okay. So now what we're gonna define a space called the unordered configuration space. So the unordered configuration space of n points is then defined to be, so it's either called CNX or U conf NX. And what it's going to be is it's going to be, um, let me move it below. So what it's going to be is it's going to be the configuration space on endpoints, modded out um, this action of the symmetric group or the permutation group. Basically, what this is saying is 2 points are equivalent if um if you can permute the positions of the 2 points to get um yeah, if you can permute the positions of one of the points to get the other point. So okay, let me draw some out for you. So example. So say you wanted to figure out what C like what the ordered configuration space of R2 looks like. So you can first draw R2 and then you can look at the condition. Okay, you need X. Um, so a point in this space would be XY such that um, like this for this condition, this just translates to X not equal to Y, right? So basically you just remove like this line. Oh, it should be this line, right? You just remove the X equals Y line.
Why? Why does that suddenly make it unordered?
No, no, so this is still ordered. This is the ordered configuration space. Um, yeah, and then the corresponding unordered configuration space, um, the corresponding unordered configuration space, what it does is, okay, you have this point over here. Actually, this would be the for R, sorry, not Rn. Okay. So you take a point, let's say this point has coordinates -1, 1, and then you set it equal to this point over here that has 1 comma -1 because now you permuted the elements, right? And you make these equal. So what that means is you basically just take this space and then you fold it across this line. And what you end up with is the upper half plane. So this is what you end up with. Okay. Does that make
Can you
sense?
not still technically order, like if you were to just sit there and objective and just plot points, you can't just define an order?
I mean, here order means that like the order in which you put the elements does not matter. That's what order means. So it's
So
not like an order in the set theoretical sense that I can order a certain set in a certain order. This is more like how a set is unordered, you know? A set is unordered, but a tuple is not unordered. That
unordered. Okay, sorry. Can you read it? So it's just like no matter which way I put it in, it doesn't matter. Therefore, it's ordered.
no, so it's unordered because it doesn't
Okay.
matter. So like for example, the set 1, 2 is equal to the set 2, 1, right? Like the notion of a set doesn't have a particular order attached to it. And the way I like list off my elements doesn't matter. So that's what like unordered means. But the tuple 1 comma 2 and the tuple 2 comma 1 are different because there it matters which order I put things in. So basically like unordered just means you don't care about like which particle you're talking about, right? So say I had
Okay.
a set of indistinguishable particles, then I would look at the unordered configuration space because it doesn't matter which particle I'm really looking at, right?
Right, right. So okay, so just for the unordered pair, what did you plotted 2 points for the ordered R,
Mhm.
which is -1, 1, and 1, -1.
Yeah, now these in the under the action of S2, these 2 points are equivalent because I can permute the elements of this to get the elements of this.
Oh, right. Yeah, yeah, yeah. You can just flip them. Right.
Yeah,
Okay.
exactly. And
So
because yeah,
and so in the unordered pair, you cannot permute -1, 1 to get 1, -1.
I mean in the unordered one, those 2 points are distinct because we don't have like another action. Like we don't have any equivalent saying that they have to be the same. This when we impose the additional constraint that these 2 points have to be the same, it becomes the ordered one.
Oh, okay. So if you can permute two things to be the same, then it's ordered. If you can't, then and they're distinct points, then it's unordered.
No, no. So okay. So there's two different spaces altogether. Okay.
Mhm.
Um, in the first space, you just look at the like all possible positions. Okay, where one particle is not on top of the other. Okay. If that's the only constraint you have, this is the ordered configuration space. Okay. It's just that we care about which particle is one, like particle one, we care about particle one separately from particle two and three and four and so on. Okay. Does does that make sense? So we care about which particle we're talking about.
Yeah, yeah. Actually, that's a
Now,
useful note.
now we impose the additional constraint that okay, I can permute the elements, I can permute the positions however I like, but these are still the same in my eyes. Right? If I allow this, then I have the unordered configuration space. So it's like a different space. It's not whether the point is ordered or not, it's whether the space is ordered or not. So in the case of like indistinguishable particles, I care like I don't care about the order in which I like talk about the positions. But if I had distinguishable particles, I care about the like if particle one is in which position is particle one in, which position is particle two in, and so on.
So follow up then. Since I can permute -1 to 1 to 1, -1, does that mean they're indistinguishable particles?
They're they're indistinguishable in this setting, but they're distinguishable in this setting.
Yeah, in the unordered setting, they are indistinguishable, but in
Hmm.
the ordered setting, they're distinguishable.
Yeah, so
As
they're
soon as I,
distinguishable here and indistinguishable here.
so as soon as I permute them on top of each other, I've just made it unordered.
Yeah.
Oh, okay. Okay, 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 okay. Okay.
Because now like the because it's indistinguishable, like because you don't know which particle is which, it doesn't make this like I mean it technically does make sense to say okay particle one is here, particle two is here, but it doesn't like give you any new information. So you can just talk about like the unordered pair. Okay. Does that make sense?
Yes. Yes, actually, that makes perfect sense. Thank you.
Okay, good, good, good. Um, so okay, now we talked about permuting points here, right? The permutation of points in our space is nothing but looking at a path or looking at a loop in the so permuting, sorry, exchanging points, exchanging particles rather, particles is a path in the ordered configuration space, right? Exchanging particles are paths in ordered configuration space. The reason it's in the ordered configuration space is because we still know which one is particle one and we still know which one is particle two. That's how our coordinate system works. Okay. So we can still distinguish the particles. It's just that the properties are indistinguishable. So far we haven't imposed the condition that they're distinguishable. Sorry, indistinguishable. Okay. But if you think about it now, these paths, they're not closed, right? They're not closed paths. They don't end where they start, right? So what we can do is we can take this path that's an ordered configuration space and bring it back to the unordered configuration space. And then they become closed because now the particles start where they ended. Because all I've done is I've permuted the particles. That's it. I've not done anything else, right? So, um, but this path, this path is not closed, and hence we bring it, we bring it down to the unordered configuration space. Okay. And now that we've brought it down to the unordered configuration space, it's a closed loop because my particles, they like over time, they like evolved and then they came back to where. So let's say particle one evolved to go to where particle two is, while particle two was evolving to go to particle one. At the start, they were at certain positions. At the end, they're at the position where the other particle was, which in the unordered configuration space is equivalent to the initial state. Because all I've done is I've permuted the positions. So this is a closed path or a closed loop. And hence we can talk about the fundamental, we can talk about which equivalence class in the fundamental group it lies. Okay. Um, Hence we invoke the fundamental group.
Ah,
Okay. So now we know we can talk very nicely about closed loops because that's what the fundamental group talks about. So the fundamental group is of like major interest in seeing if there are any exotic systems where we can confine paths so that particles so that we can get exotic types of particles. Okay. So it turns out, so fact is okay, and yeah, so we care about the first fundamental group, P1, pi one of U config N X, and then some point P. It doesn't matter what this point P is for now. Okay. So let's look at main examples. Okay. So in R3, so if we look at in R3, um, it turns out that pi1 of u config n of R3 at the point 1, 2, n, okay, this is nothing but Sn, okay? So this is the permutation group. And so if you remember when we were talking about the two particle system, we talked about the action of S2 or the swapping operator, right? We talked about the action of S2 on the two particles. And then from there, we deduced that the only possible representations that we can have of swapping are the trivial one and the one that multiplies like gives me a phase of -1. Okay. So we use the action. So here, so when we were swapping, we basically did an action of S2 on the particles, right? We just swapped them and then we swapped them back, right? We happy with this? Okay. In R2, however, in R2, things are different. Okay. In R2, things are very different. It turns out, however, that in R2, the first fundamental group of the unordered configuration space, um, sorry, this doesn't even make any sense. You can take P to be whatever point. I don't think it really matters. At some point P is the so-called braid group. So that's
The
called
brain.
the braid group.
Oh, brain.
Okay. The braid group is like the permutation group, but it's more free. So you can show that so this is an exercise. Show that the so okay, when we talk about the cardinality of a group, we call it the order. Um, Show that the cardinality of the group Sn is n factorial. Okay. So more specifically, it's finite. Hence, Sn is finite. Okay. And then using what we talk about below, show that the braid group is not finite.
Does that just come from the fact that in higher dimensions you have an extra degree of freedom?
Yeah, yeah, that's basically what it is. Because I mean, your world line lives so in three dimensions, your world line lives in R4, but R4, and then you like mod out, okay, two particles can't be on top of each other at the exact same time, and stuff like that. And then after you do all those reductions, um, you still have a lot of room to move around. But in R2, like removing those extra things, um, forces you to sort of like you can't like move freely basically. And so you get stuck in certain places. The best way I can describe it is okay, say you're on a line, right? And you have two particles moving this way and this way. Those two particles will hit each other if you're constrained to move on a line, right? But if you're on the plane and the two particles, you can just make one particle jump over the other, right? Because you're in the plane. So you have this extra degree of freedom, like you said. And that's where this comes from. Okay, so now in configuration, sorry, the exchange. So when we talk about exchange statistics for um, particles constrained to move in R2, we have to look at actions of the braid group on the two particles. right? So in R3, we looked at we look at actions of Sn on the particles. And this is we look at the action of Sn because that's what the fundamental group of the unordered configuration space for R3 is. And then in R2, we look at actions of Bn on the particles. Okay. So one we have a finite group and the other we have an infinite group. We just moved down one dimension and it already added so much more complexity. So in some sense, particles constrained to move in R2 are more they have the possibility of being exotic, whereas particles in R3 are pretty boring. Um, Mathematically boring. They're not physically boring.
Can I
Uh,
ask a question?
yeah, yeah.
Why why is that significant? Why would you want to study something in a lower dimension rather than a higher dimension?
I mean, there's many reasons, right? Like, for example, when you're making smaller and smaller transistors, you basically so okay, so firstly, you can't really have a particle constrained to two dimensions, right? Um, but what you can do is you can sort of reduce the scale so that it doesn't really move up and down that much. So it's basically living in two dimensions, right? So I'm guessing. I haven't really looked into this application, but one place that I'm guessing this might come up is if you're making transistors and you want to make them more space efficient, so you make them smaller and smaller and smaller. Firstly, there's a limit because of quantum tunneling, right? There's already a limit to this. But then does is there like a more fundamental like is there another fundamental reason that you can't do it? And you then want to look at does the properties of the electron change when it's constrained to move like in a space that's basically two dimensions? Does that make sense?
So it's basically looking at the fundamental property of the electron
Mhm.
in two dimensions.
Yeah, it's like do the fundamental properties of particles depend on the dimensionality of the space they're allowed to move in, or is this something that's already like if an electron is in three dimensions, would it behave exactly the same as an electron in two dimensions? That's basically the idea.
Oh, so like if I took a snowflake, right,
Mhm.
and I took like the D6 group of the snowflake
Mhm.
and I moved it down to two dimensions, would it still be the same group?
I mean, the group is the same. Like Sn has a lower dimensional analog. Like S2 is a lower dimensional analog of Sn.
It's just without the North Pole, right? Or something like that.
It's more about like you're not looking at the group itself, but rather the action of a group on another space. And you care about the dimensions of that space and not the group itself.
Okay.
You're
So
looking
it's
at the properties of the space by studying the actions that various groups have on the space, rather than talking about the group itself. So in this case,
okay.
again, you have like your electron, which is constrained to move in two dimensions, and exchange statistics are given rather than by the permutation group, by the braid group. And you're seeing that, okay, is this physically what we see or is it not? I think there are a couple profs at U of T that do this. I'm pretty sure Boris Braverman and Sergio Della Bredera
Oh,
are
the quantum prof.
yeah, are they're looking for particles in two dimensions that behave not as fermions or as bosons, but rather as anyons. That I'll define like in a minute. Are there any other questions?
So they're just looking for particles that aren't fermions or bosons.
Yeah. And mathematically speaking, they must exist. Purely mathematically, as we'll see in a second. Um, they must exist. Okay. So now let's look at defining properties of Sn. So one can define Sn. Okay, so I'll leave this again as an exercise. It's a fun exercise. Show that. Okay, so I'll define sigma I to be the permutation to be the permutation that swaps I and I plus one. Okay, so it just swaps I and I plus one. Show that Sn has the following properties. So firstly, if you take sigma I plus one, sigma I, this is the same thing as taking sigma I. Let me just make sure. Yeah, sigma I plus one, sigma I plus one. And here I is between 1 and n minus 2.
Why is n minus 2?
Because when you do n minus 2, this becomes n minus 1. And so you're swapping n with n minus 1. So
Uh,
yes, it's like sigma n isn't really defined. I mean, you could define it as like swapping 1 and n, but I think something changes. I'm not too sure. Another one is sigma j equals sigma j, sigma I, when the distance between I and j is more than 1. Okay. And finally, squaring sigma I gets you the identity. Okay. One fact now that I will that okay now so that's the symmetric group. I mean the symmetric group is very nice. So doing the same permutation twice um undoes the permutation fully. And so in some sense the order um of which string is on top of another string doesn't matter, right? So for example, so here if we see, right, we have that this string is on top of this string, right? And then this string is on top of this string. But at the end of the day, the particle ends up where it starts. So in so this is equivalent to the to like to this diagram. Okay. So like it doesn't matter if one string is on top of the other because you can just deform it so that they're both straight. But in the braid group, it does matter which is on top of the other because you don't have the extra degree of freedom to pull that braid out and then like stick it back in into a different order. So, so what that means is, what that means is, say you have two particles like this. Let's say you have three particles like this, right? Actually, let's just look at two particles. So you have this braid, and then um you have this braid. So in SN, these braids would be the same. But in the braid group, these two are not the same because in the left one, so in this one, the right braid is on top, and in this one, the left braid is on top. Okay. And now the okay, so does that make sense? Are we okay with this?
yeah, so far.
Okay. Now we can define the braid group in a different way. And the way we'll do that is by looking at diagrams of this form, okay? And then defining a group structure on this, okay? So, So let me give you an ex like I so s- so say we have 3 points and then we have like some braids, right? Like this is a braid. Um, in 2 points, this is a braid. We also have like more exotic braids that look something like that, right? These are examples of braids. So the braid group is the collection of all such braids, and then we define like a group operation where we just stack one braid on top of the other. Okay. So what I mean by that is, for example, so define, so these are examples of braids. So define operation on Bn.
Is it just in R2?
What the braid, like braids being like this?
Yeah.
Um, so the way I'm defining it right now, no, I haven't made any like um implicit assumption about like what the braid group is, like what the underlying space is, right? I'm just saying that like the order in which I braid matters. So there's no like underlying space. Um, but you can talk about um you can use this notion over here. Where is it? You can use this notion over here to talk about braid groups. So this is called the braid group uh, on X, right? So the braid group on R3 is just the symmetric group. The braid group on R2 is the braid group. Then you have the braid group on the sphere, which is sort of in between the braid group on R2 and the braid group on R3. Um, So there's no like notion of underlying space when I'm just talking about like braids as strings. Like I'm not like implicitly using an underlying space. All I'm saying is that like the order in which I draw the braid like matters. That's basically what I'm saying. So yeah, we can define an operation on this braid group um by just stacking one braid on top of the other and then seeing the resulting braid. So for example, in the three-dimensional braid group, I can take the braid that goes like this, and I can multiply it by the braid that goes like this. And then this thing, so what I do is I take this braid, I stick it here, and then I take this braid, and then I stick it here, and then I look at the resulting braid. The resulting braid looks something like this. So I go like that, and then I stop there, and then I go like this, this. So that's what the resulting braid looks like. Um, okay. So then this is now almost a group. Um, so for groups, we also need inverses, right? Um, but remember, I can't just do the same like braid again, right? Because the order of the braids matter. So in SN, I can just do the same, I can just put the same diagram again and I get like the straight lines that I want. But in the braid group, um, say I have the braid of two particles that goes like this. The inverse of this um would be the group, oh sorry, would be the braid that has the right particle going over and then the left particle. Because this thing then gives me, so I know that it has to look something like, so this, so it goes like that, and then it goes like that. But you see that the the left string, what I mean by the left string is the yellow string is always under, right? And since it's always under, I can just pull it all the way out because it's always under. So this thing becomes like that.
So this is just a really complicated way of tying shoes.
Yeah, exactly, exactly. It's like in a shoelace, it does matter if I put like if one lace is always above the other, I can just sort of separate them, right? Because they're non-interacting.
Yeah,
Um,
but as soon as they're knotted together, they're interacting and one is
yeah,
under. Yeah, okay.
yeah, exactly. So it's just like a mathematical description of what it is. So okay, doing all these, we get a group, and this is another example of a braid group. Yeah. So defining braids as like collections of these graphs um, gives you a braid group. Yeah, so it turns out that you can generate this braid group by, so okay, I'll just copy this. Oh my God. I'll just copy this. And then what I'll do is I'll remove this Sn and I'll put Bn and I'll remove this final condition. Okay. I'll remove the condition that squaring the braid gives me the same thing. So let me draw an example of why we need to remove that condition. So say again, I have the two particle braid and I have this braid, and then I put it on top of the same braid. This new braid, if you see, is like, looks something like this. You see, it's sort of knotted together, right? And because it's knotted together, it's knotted in a non-trivial way. So one braid goes on top of the other, then it goes under the other, and then the first braid goes over and then under. So I can't really, swap them out. So so the braid group and the symmetric group are basically the same group, but the I impose like an additional condition that my braid group, sorry, a squaring a braid doesn't give me the same braid. So it doesn't give me the identity braid. Does this make sense? Does all of this make sense? So this is so I can define the braid group equivalently like this. And then you can now then show that um, Bn is nothing but the unordered configuration space of n particles. Okay. So that's like the main thing I wanted to talk about. There's one final thing that I'll just mention, and if you want, I can prove it because it's been 2 hours. So if you guys are getting tired, I can stop it here. Um, but if you want, there's
Not
like
that it's not that I'm getting tired. In fact, you know what? If we could talk about this all night, I'd be so down for that.
yeah.
The only thing is I have plans at 8. So yeah.
Okay, okay. Let me like just go very quickly now. So now let's look at so basically the question now boils down to what are the possible representations? What are the possible representations of Sn and Bn that are um, so we need them to be unitary because we're talking about quantum systems. We need them to be unitary and um, that act on on C. Because remember, the wave function is complex valued.
Mhm.
Right? What are the possible representations? So let's see, Sn. With Sn, it's actually very easy. So um, So let's say our representation was raw. Now, taking a particle and swapping it and then swapping it back, right? Is so remember, by the definition of representation, this thing has to be the same thing as this, right?
Isomorphic, right?
No, they have to be the same because It's a group homomorphism. So this is the like by group homomorphism.
Isn't that isomorphic or like is group isomorphism something else?
I mean, a group isomorphism is a group homomorphism that is bijective
Okay.
and whose inverse is also a homomorphism. But you can, I mean, Sn and the unitary group are not isomorphic groups because one is infinite and one is finite. So it, I would like recall the definition of representation. So okay, a unitary operator on C is the same thing as multiplication by e to the I theta. So then this representation is just e to the 2 I theta for some theta. But remember, in Sn, this operation is this is the identity, right? So what this tells us is that rho of identity is e to the 2 I theta, but identities must map to identities. So what this tells you is that e to the 2 I theta equals 1. And this is what we talked about above. So this is the fermion boson thing. Okay. So in the case of Sn, the only unitary scalar representations of Sn are either multiplication by 1 or multiplication by -1. For Bn, it's a lot more complicated, so I won't. I'll give you guys resources if you guys want to read about it. But you're allowed any theta. And the reason sort of boils down to the fact that you here the main step that like did all the reduction was that sigma I squared equals the identity. And because sigma I squared doesn't equal to the identity, there's no additional restriction that you have, right? So all you can have any theta. So one, if theta equals pi, um, these are called so if theta is so if theta is zero, firstly, if theta is zero, this is these are bosons. If theta is pi, these are called fermions. I've written fermions. And finally, if theta is else, then these are called anions. So anions are nothing but particles constrained to 2 dimensions that when we swap them, we pick up an arbitrary phase factor.
Is
And
this like a
this,
unrelated question? Is this like a motivation for gravitons?
I'm gonna be honest, I have no idea, but I can look into that if you'd like.
Actually, yeah, that would be great.
Okay. Um, so yeah, um, this is why the fundamental group is of interest to physicists, at least, is because with studying the fundamental group and studying representations of the fundamental groups on exchanges, um, we've found theoretically that you could have particles that, when exchanged, pick up an arbitrary phase factor. Okay. I hope I have motivated why we care about the fundamental group. If not, please let me know if you like what questions you have so I can like answer them. Because understanding this is, I mean, again, this is not really related to what I want to talk about a month, like a couple months from now. But this is one of the reasons why I think it's important to at least know concepts from theoretical math when you're studying like theoretical physics. So yeah, are there any questions that are related to like what we talked about right now?
No, actually, I think you got to all of mine.
Okay. Are there any questions you have, Sting? Okay.
Yeah, I got to digest a lot of contents now.
Yeah, no, so
Yeah.
basically what I've described here are 4 pages from a textbook that I used that like one of the DRPs I was in last year used, and I had no idea what was going on. I'll be completely honest. I had no idea. It took me quite some time sitting with this and like trying to make sure I understood everything that's happening. And then once I related it to like concepts I knew from before, I think it makes a lot more sense. So I would recommend just like reading over the notes once again, looking at the recording once again. If you have any questions, you can always just message me and then we can talk about it.
Right.
Okay, and so
Oh,
next week we'll jump into linear algebra, um, and multilinear algebra. I think I'll spend about 3 meetings on that. Um, because from the poll I did, most people seem to be okay with multivariable differentiation, so I won't spend too much time on that.
yeah. There. Yeah. Okay. Okay. So I gotta. Oh. Yeah. Multivariable differentiation is not that bad. Sorry.
I mean, again, we're going to restrict ourselves to working in the smooth setting. And in smooth setting, like everything that you would hope is true is probably true. Um, when you talk about lower regularity, things sort of get a little weird. Um, but the only things you really need to know are that like in the smooth case like um, partials commute, the derivative matrix is given by the matrix of partials. Uh,
Yeah. 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 The Jacobian and the
yeah,
Hessian and stuff, right?
yeah, that we'll only care about the Jacobian for now. We'll see the Hessian and the Laplacian when we talk about Riemannian manifolds.
Okay. Okay. Okay.
Because um, the Hessian requires additional structure to like talk about. Um, have you guys ever seen PDEs? Like any PDEs?
Yes.
Heat equations.
Okay, you've seen the heat equation. Okay, okay, okay. So yeah, a big field of study in Riemannian geometry is studying the heat equation on
Um,
fold. If you guys are interested, Marco is running a course that I'm also in right now, where he talks about the Schrodinger equation on an arbitrary Riemannian manifold.
That. Like, what's the code?
MAT 1312.
Okay.
that's graduate level.
Yeah, yeah. Okay, so the
Sheesh.
prerequisites are differential geometry.
Oh, that's fine. We'll just pick it up as we go along.
I mean, you should hopefully know everything by this time next semester. You'll know everything you need to know for to take that course.
Matt 363, right? Or 367?
So you need 367.
Yeah,
Um,
to be honest, I don't really see that being too difficult after taking this stuff because this is exactly what we're talking about there anyway.
yeah, so 367 will talk. Let me just end the recording so that we can.